So the way I see it, we've made it through 2 units of this class so far. I think of this class as kind of being divided into 3 different stages, where the first stage is really data science. It's data wrangling, data visualization, some of those data set oriented skills. And then in the second part of the class, which we've now moved through, we've done some programming skills. We've learned how to write functions, use iterative programming, and kind of work in this package structure and with GitHub. And so now I'd like us to move on to what I think of as the third unit, which is to do with statistical analysis. I know that data science is kind of the hot word right now, the hot thing, but really, statistical analysis is the core of where R is powerful. It's what this language was developed for, and it's what we're going to do with the next 3 weeks of this class. So let's talk this week a little bit about statistical distributions and how we simulate data from them. So first I want to review these concepts. Hopefully you remember some of this from previous classes or experience, but let's just make sure we're on the same page here. So when I say a statistical distribution, this is meant in reference to what's called a random variable. And a random variable is kind of a quantity that we don't know the value of until we take a random sample. And there are a few ways to think about this. You can kind of think of the randomness as being inherent. So one example that's common is a coin flip. You can think of the results of a coin flip as a random variable. We have an idea of what could happen. It could be heads or it could be tails. But until we actually flip that coin, we don't know what it's going to be. And if we flip another coin, it might be a different answer. Another common example that you might think of the randomness as not coming from the quantity itself, but from which sample you collect. So we can think of people's heights, right? We have some idea of how tall people tend to be. Most people tend to be somewhere around 5'7", but of course there's a lot of variance there. And you can't tell me how tall the next person who walks by my window here is going to be. Not until we actually see that person walk by do we know the value of that person's height. And similarly, we might think of income of US workers. We have some range that we have a good idea of the annual income must fall in that range, but we don't really know an individual's income until we grab that individual and check out their tax returns. And so this is important because we need some way to describe these random variables. Although we have not yet taken our sample, we need some way to summarize what could happen. And that's what a distribution does. A distribution refers to really any way that we have of communicating what are the possible values this random variable can take, and how likely are we to get those values. So it's very simple in the case of the coin flip, right? We have 2 values, heads or tails. Sometimes we'll associate the numbers 0 or 1, something like that. And we know that for a fair coin, there's a 50% chance of heads, 50% chance of tails. That sentence right there, that's one way of summarizing a distribution. But it gets a little more complicated when we're talking about continuous distributions. When we're talking about something like height, where I can't possibly list out all the values of the possible heights people could have. And so instead we usually draw a picture. We usually draw a shape that kind of describes what typically happens with height. So here's an example. And now height and gender is actually a very nice construct for explaining things, but it's also very frustrating because I hope we're looking at this plot and saying, look, there's not necessarily 2 genders. How did they know these people's genders? It's a little bit of a tough example, so I hope you'll forgive me for oversimplifying here with this plot I found online. But what this plot is illustrating here is that presumably someone gathered a sample of many men and many women and measured their heights, and what we can see here is like around 80 people had a height of about 66 inches among the women, and about 50 people had a height of 71 inches among the men. And so we make these bars in this histogram and we say kind of what's the shape? And we can sort of see that for both of these gender identities, we have this kind of bell curve shape. Some people are shorter than average, most people are right around average, and some people are taller than average. And it's kind of symmetric, right? Most people are near the middle, but some people fall on the extremes. So this picture here, or this shape, is one way we can describe a distribution. We can say, look, the distribution of heights comes from a graph of this shape. Similarly, we might talk about the distribution of income in the US, and while we know that it might be anywhere from $0 to $1.6 billion a year, Most people don't make anywhere near 1.6 billion. Most people make under 100,000. And we could sort of document where the typical incomes lie. And we could get a shape there. So here's from the 2014 census. Here's the estimate of household income in the United States. And so we can see here in 2014, half of households made under $53,000 approximately per year. Half of households made above that. And so this is not quite the same shape, right? This shape sort of trails off into the distance, so it's not a bell curve, but it is its own shape. Fun fact here, I did the math on this. On my screen, the distance from 0 to 200,000, so that 95th percentile, that distance is about 5 inches. Just for fun, because you're forced to watch my video, I'm going to ask you to point on your screen to where you think Jeff Bezos is, the richest man in the world. Where would he be on this plot? If you pointed anywhere on your computer screen, you're wrong. In fact, if you pointed anywhere that you can reach, sitting wherever you're sitting, you're wrong. I did the math, and Jeff Bezos, $1.6 million a year, is about 3 feet that direction. So it's kind of over by my refrigerator if you were at my house right now. So we have this distribution, and it visualizes some things that are important, right? We have a random variable that says if I sample someone, what is probably going to be their income? And a good bet would be to say, oh, they probably have an income somewhere around $50,000 a year, or at least their household does. But there's always some minuscule chance that you'll sample, oh, I don't know, Jeff Armstrong, president of Cal Poly. And there's some even smaller chance that you'll sample Jeff Bezos. That's how you read these distribution plots. Now, because these plots have shapes, and the shape is kind of how we describe the possible values of that random variable, some distributions come with names. And so what you've heard in other classes when you've heard of things like the normal distribution, that's just describing the particular shape and the particular equation behind the shape of that plot. And so for this class, I'll ask you to be a little bit familiar with a few distributions. You don't need to know any underlying math. You don't need to know anything sophisticated. But I do want you to have some familiarity with these 5 distributions. So I'm going to go over that right now. The uniform distribution is kind of the most basic one. And this is one where if you know the range of values that could happen for that random variable, but you know pretty much nothing else, you might assume that it comes from a uniform distribution, that all the values in that range are equally likely to occur. And so here's an example. The gray bars there are a random sample I drew. We'll talk about how to do that in a moment. The blue bar here is the actual density, it's called, the actual shape of that distribution. And so we can see here that, of course, when you randomly gather a sample from data, it doesn't magically perfectly fit the shape, right? Those heights we saw didn't perfectly fit the bell curve. But it's kind of reasonable to assume that in a perfect world, this is sort of the shape that the data is coming from. So uniform is boring, it's just a straight line. It says everything is equally likely. The next most common that you have seen all the time, I'm sure, is the normal distribution. We're going to get up close and personal with the normal distribution in the lab this week. You will learn why I have a tattoo of the bell curve on my back. But for now, we're just thinking of it as anything that happens to take on this bell curve shape. And this kind of occurs when you reasonably expect values to fall pretty close to the center. Like there's some average happening, like an average height, and most people are kind of close to that average. Now in real life, and when we get to the unit on hypothesis testing, we'll talk about the t-distribution. For all intents and purposes, you can pretty much treat the t-distribution as identical to the normal. It's just a bell curve shape. And it comes about in the same context that the normal distribution comes about. We just see this one a lot more often in real data. For the curious, when the standard deviation of the data is unknown, we have to estimate it, and we end up with a t-distribution. It makes the bell curve slightly wider, it's a little fatter, it's really not noticeable, and you can interpret it just like the normal. So we're looking here, and there's some average value at 0 that is most common, and other values tend to fall close to that. Here the blue line is the t-shape, and I just added on there that red line for you so you can see that the normal is indeed slightly different, slightly narrower, not that important. Now the weirdest distribution I'm asking you to know about is the chi-square distribution. And the shape of this, honestly, is not as important as the others. But we are going to use this distribution for hypothesis testing, so I want you to see it here. A couple important points about the chi-square distribution. One is it's what's called skewed, which means that that tail is trailing off into the distance. It's not quite symmetric like a bell curve. It's something where we have many extreme high values, much like Jeff Bezos. And this is used, and also this can only be positive values. The chi-square distribution can only take on positive values, 0 or above. We'll use this when we test count data, when we do some tests on categorical variables. And so keep it in the back of your mind for now. And last but not least, the binomial distribution. This one comes about when you have a situation with two possible outcomes. The most common example out there is maybe voting. You have to vote yes or no on a certain proposition. And so you might need to go out and count how many times each outcome occurred. You might count how many people say they're going to vote yes on proposition A. And so in this example, I've got a count from 10 people, right? And I want to know how many said yes. And so in one of my trials, only 4 people said yes. And then in about 100 of my trials, I did 1,000 here, we had 6 people said yes. In most of my trials, 8 people said yes. And so the value of the binomial random variable is a count. It's a number out of the total where the outcome occurred that you're looking for. Keep that voting and keep coin flipping in the back of your mind for binomial, and I think it'll be a little clearer. So why do we care about distributions? I just gave you a crash course on introductory statistics. I hope it wasn't all new to you, but of course, feel free to seek out other readings if you need a little brush up. But why do we have to care about this thing in a world where computers can do all the computing and the math for us? So a few things that we use this for. One is to find the probability of an event. Something's about to happen. We would like to know how likely the outcomes are. Maybe if you go to Vegas, if you're over 21, you might be interested in this approach. So this is when we ask questions like, if I flip 10 coins, what are the chances I get all heads? The number of heads in those 10 coins is a distribution, or is a random variable, and it has a distribution. We just learned it. It's called binomial. How many times did I get that success of heads out of 10 tries? And so if I know that it's a binomial distribution, if I know the shape, then I can use fancy math or computers to find how likely it is that all 10 of my coins are heads. Another thing we often want to do is sort of estimate the percent of a population. So I might be interested in saying, what percent of people are above 6 feet tall? Maybe I'm making a basketball team. And so I know the distribution of people is kind of a bell curve, and I can say, okay, where on that bell curve shape is the 6-foot cutoff? And so what percent of the area under the curve, what percent of the density of that shape lands above 6 feet tall? And so here it's not predicting something, right? I'm not talking about randomly going and sampling people. I'm talking about guessing the percent from that population. And then lastly, and probably nearest to my heart, we use these statistical distributions to quantify our evidence. Statistics is all about saying, I have data, what can I reasonably learn from it? And so I might say, I went out, I surveyed 100 people, 67 of them said they planned to vote for Measure A. Do we think Measure A is going to pass on the ballot? We don't necessarily know that these 100 people are the only ones voting. Presumably thousands and thousands of people are voting. So we don't know for sure that Measure A is going to pass. But has this survey we'd just done given us confidence that we think that's going to happen? What did we learn from that data?